Podcast. This is Mr. White.
Mr. Johnson.
And today we're going to revisit strings.
So we're getting the band back together.
Yeah. I don't think they get that joke.
No, but okay.
So, revisiting strings, meaning that we already saw these things once, right? So, way back last week, we talked about what if we increase the tension and decrease the tension. What if we increase the length of the string, decrease the length of the string? If we recall, we remember that by increasing the tension, the frequency went up.
Right.
And therefore the pitch went up. So tension to frequency was direct. So that means frequency and pitch would have to go down. Length, on the other hand, if we made the string longer, do you remember what happened to the frequency and the pitch?
Well, they both go down.
They both go down. So length is inversely related to frequency and pitch. And by making the string shorter, then the frequency and the pitch have to go up. So this is just a rehash so far from last week. Some things, though, that we wanted to talk about, and maybe we saw in the spring investigation. One thing would be the speed of a wave, where we talked about how the speed of a wave is equal to the frequency times the wavelength, measured in meters, Greek letter lambda, upside down y. Frequency was measured in hertz, which is just 1 over a second. We saw that. And we're trying to measure the speed of a wave in a string, which is kind of tricky. And you know, if the spring was stretched out or not stretched out, if you had a slinky or you had one of the helical ones, if you had one that was kind of broken or one that hadn't been touched. I mean, there was a lot of variables there.
Right.
So what I'd like to focus on to start is the speed of sound. And so one question I got in class a lot was, does the amplitude affect the speed of the wave? So does how much you moved the spring affect the speed? And my question back to the students was, does loud sound travel faster than quiet sound? Does bright light travel faster than dim light?
Well, the light one I know right off the bat, because
What's
you
the
can see
answer to
it.
that?
It's no.
No.
Light travels
Okay.
at the same speed.
And so when students will answer one of those questions, and I come back with, they usually get no for one of them right off the bat. And I come back with, well, do the rules of physics change for each observation, or do they stay the same? And do we realize that a wave is a wave is a wave?
It's very poetic.
Very.
Well, I mean, I guess a wave is a wave is a wave. I mean,
Okay.
that's the way it is.
So loud and quiet doesn't matter. All travels at about 340 meters per second.
I mean, yeah, because if you actually think about it, if you were at a concert and somebody's playing loud music, or you're somewhere same distance away from a stage and someone's talking softly, you still hear the sound instantaneously. It's just the pitch,
Right.
whether it's loud or soft.
So the loudness, the pitch, all of that, none of that affects the speed. So loud and quiet, what do we go with? Bright
And dim.
and dim, okay, don't affect the speed. It's a really important concept for the students to get, because I think there was some confusion about that, because we had you use your phones to measure time,
Right.
and those weren't very precise devices. Well, it was off by 0.2 of a second. Well, my question, what's your reaction time? How good of a timing device is your phone providing you, etc.?
How much charge is in your battery to actually press the button?
Yeah, there's so many factors that go into that. But None of this matters.
No.
Amplitude don't. Amplitude don't affect the speed. There's nothing wrong with that at all.
Nope.
Nope. The other factor that we tested today in the investigation was the thickness of the string. And so you do your setup, so you've got your cup, and you've got your string, and it hangs over this pulley, and it's got some weight. And you pluck the string, and you made some noise. Well, if we wanted to test for thickness, our cup would have to be at the same place. Our pulley in the same basic place. The amount of weight, whatever it is, has to be the same. And so what we would have to test for is how thick is our string going to be. So what if the string was really thick?
Wow.
Versus what if the string was really thin? And that's a perfectly legitimate question. So we've kept everything the same. So what should they have discovered in their investigation today? I should label that, just in case. Thick. What should they have discovered? Was there a difference in the sound?
Absolutely, yeah.
Yeah. Which one produced a higher pitch?
The thinner
The
wire.
thin. So thin led to a higher pitch, therefore a higher frequency.
Mm-hmm.
Thick led to a lower pitch, therefore a lower frequency. And so there's a lot of ways to adjust the notes that come out of a guitar. So we've talked now about how much tension you put on the string. We have talked about changing the length of the string by pushing down on the frets. And now we're discussing the thickness of the string. A whole nother ballpark could be the material. If you had plastic versus the metal strings we provided, then you could even get into the types of metals, what kind of sounds they would produce, etc. Just something to consider as we work through this. We also did this activity where there was some tape on the floor. And there were like 30 pieces of tape. I'm not going to get 30 lines on here. But you were given some instructions like, hey, this is time 0, and at time 1 we want you to take a step. And at time 2 we want you to take another step. And at time 3 you take another step. And that seemed to be the pattern. And you were asked some questions about wavelength and frequency and so on. So what is frequency, Mr. Johnson? Do you remember?
Frequency is the amount of the number of waves that pass a certain point in a certain given time.
Okay, so how many waves would get from point 0 to point 1 in 1 second?
1.
1. Yeah. And how many waves would get from point 0 to point 2 in 2 seconds?
2.
So the frequency would be 1 wave for every second.
Mm-hmm.
What if we jumped 2 steps every single second?
And the frequency would be 2.
The frequency would be 2. And the wavelength would be
0.5.
Could be. I guess we didn't define a distance.
Oh.
I'm sorry, we didn't label this. This is measuring time. My bad. So, what if you were to go 3?
Well, then it'd be 3.
Yeah. And so we've increased the frequency, and what ends up happening is we realize that the frequency and the period are inversely related. So as the frequency goes up, the period has to go down. Or as the frequency goes down, the period has to go up. And so we keep investigating all of these different things that keep showing up in waves. These are properties that show, and measurables that show up in waves, whether they're sound or light or springs or whatever. And then there was one more thing, and we're going to leave them to do the sample problem in their reading packet. But the last thing we wanted to talk about today was the standing wave. So this investigation is always interesting to see what the students do while they're waiting for their partners to write stuff down. And I guarantee you, 9 out of 10 groups, there's a student at one end of the spring, there's a student at the other end of the spring, and what do? They try and pulsate the spring back and forth as many times as they can, and something magical seems to appear. They have accidentally created a standing wave. Now, they don't know it's a standing wave, but a standing wave looks like this. And it's moving so fast that it is its own reflection. And so it's like you see the wave appear at multiple points at the same time, with the exception of these points right here, which appear to be stuck in time. And those points, of course, are called nodes. And these other points, where there always appears to be a maximum or a minimum, these are called antinodes. And as a result, you can see these waves, but when you hear a musical note, you are hearing a standing wave. If you don't hear a standing wave, you're hearing a note that is not in tune. You know what are the terms for notes that are just a little out of tune? They can be flat or they can be sharp. And that means if it's flat, it means you've got not enough. Okay? It means that your wave accidentally kept going. And this is the end of your musical instrument and we can't quite get it in there. So this would be flat. If it's sharp, it means that you've got too many waves. So it would come up short. And now this extra bit that you get here, this makes you sharp. These are not good things in music. Standing waves means that you are in tune. So I think maybe we've covered everything as it relates to frequency and wavelength. Did I miss something?
No, my notes are missing something.
And standing waves. So with that said, this is signing off on the Section 3 podcast. This is Mr. White.
Mr. Johnson.